Hello, good people. Welcome to section 3.3. I have the camera turned off because I'm going to need the screen to be flat because I'll be doing a lot of writing as we take the derivative implicitly. So the topic of this, or the big idea in this topic, is how sometimes when we have to find the derivative, we don't have an equation for the function that we want to find the derivative of. And that's probably because the function really isn't a function, it's more of an equation. So, a couple of things to keep in mind. Number one, when we ask for the derivative, remember we're asking for the derivative, we're asking for the slope of the tangent line at a specific point. So, if I have a function like this, and this is f, the derivative would be, for example, at this value, and I'm just going to say that this is 4. The derivative, f prime of 4, would be the slope at that point, x equals 4 on the curve. So the slope of that tangent line, the slope of this purple line, would be the derivative value, right? But I don't need to have a function in order to find the derivative. So what if I have a circle? And we'll pretend that that's a circle. We'll say that that's a circle. If I tell you to find the derivative at x equals 0, well, the derivative at x equals 0, when x equals 0, f prime at 0 would be 0, right? Because we're saying that at this x value, the derivative, the slope of the tangent line is 0. And not only for the top point, but also for the bottom point, the slope is 0. And so I guess what we need to consider is we can find the derivative value if we're saying that the derivative is the slope of the tangent line of functions, of graphs, I should say, that are not functions like this one on the right. So this is not a function because it doesn't pass the vertical line test. This is a function, and yet I'm able to find the derivative of both. Okay, so that's the first big idea. I said I don't necessarily need a function graph in order to find the derivative. If I can find the slope, that would be my derivative. The second thing is usually when we are given equations, we're given equations in this format where I might have, and I'm going to make a chain rule composite situation. So I have a composite function, e to the x plus 5x to the third to the fourth power, we'll say. So I am given the equation y equals, and then everything on the right side is in terms of x. My variable is x. And when I ask you to find dy dx, I'm asking you to find the derivative of the y equation with respect to x. And what that means is I'm going to find the derivative of the y equation, and I understand that my equation is in terms of the variable x. So how would I find the derivative? Well, the derivative would be the derivative of the outside, the derivative of the outside. So here's my outside function. So I would take the derivative of the outside with the inside still in it, and then multiply that by the derivative of the inside, which would then be this. Notice I'm putting both terms in parentheses to signify this whole thing is the derivative of the inside, and I'm multiplying that times everything else. This is how I would usually do it, right? Or I could say there's this function, h of x, that is the square root of tangent x, and I want to find h prime of x. So the derivative of h prime would be the derivative of the outside, which is the square root. Now remember, the square root is also the 1/2 power. And so when I take the derivative of the outside, I would be taking the derivative this way with the inside still in it. So tangent x is still in there, times the derivative of tangent x, and the derivative of tangent x is secant squared x. So that should make sense, I think. This is what we've been doing with the chain rule in the last couple of days. So now what implicit differentiation says is, what if we had a function in terms of x. We were taking the square root, just like this one, but I didn't know what the inside function was. And instead, I call that inside function y. How would I take the derivative? How would I find h prime of x if I didn't know what my inside function was? But I knew that it's in terms of x because I see h of x. So that means this isn't my variable. This is the name of the function that uses this variable. Now, in our previous example, we know that y is tangent x, right? But how would I find the derivative of this? Well, I would still find the derivative of the outside. So the derivative of the outside would be 1/2 times something to the negative 1/2, with the inside still in it, times the derivative of the inside, which would be y prime. Some people, instead of writing y prime, they would write dy dx. But that's the same situation that we did here, right? Like these two are following the same rule. And that's what implicit differentiation is going to tell us, that sometimes we don't have one of the functions, the inner function, or my equation might not be in terms of y equals something. I might have x's and y's mixed up. That's okay. But every time we see a letter, and I'll call it a letter, every time I see a letter, that's not the variable of differentiation. That's not the variable that the function is in terms of. I'm going to have to treat that letter, that quantity, as a function of that variable. And this is what implicit differentiation is going to teach us, is there is a way to do it. And as long as you follow this chain rule, because this is really how we're finding the derivative of something that we don't know what the inside function is, we just set up the formula. That's what we're going to do with implicit differentiation. So in video 2, we'll start the notes and you can see how that works.